All right, let's go. So what did we do last time? So we talked about regressions. So this is the regression of the variable y on the variable x, also known as conditional expectation. Okay? And remember, this is a random variable. It's not a number. Right? It's a random variable taking the same with x as the input. Now sometimes, so if linear, that is, this thing is a line as a function of x, we showed then that line is actually, so there was nu plus c over sigma squared x minus mu. This is what we proved last time, where nu is just the expected value of y overall, mu is the expected value of x overall, sigma squared is the variance of x, and c was the covariance of the random variables x and y. All right? So we proved this theorem. Remember, if it's linear, then the only way that it's linear is like this. Or another way of writing the same thing, i.e. mu of y given x is mu c over sigma squared. That's alpha. This was alpha. Plus c over sigma squared x, where this is beta. Just reminding you what we did last time. All right. Now, suppose, so this was probability theory. This is purely, there's no samples here, there's no, given the outcome, what can we learn? Now let's do a little bit of statistics. Okay, so assume that the regression of y on x is indeed linear. Can we find estimators for alpha and beta? So we observe ordered pairs like x1, y1, x2, y2, and so on. So we observe these pairs. So oftentimes you'll see people do a scatter plot. So here's the x values and the y values, and here's x1, y1, and here's x2, y2, and here's x17, y17, and there's a whole bunch of dots in between. And, well, maybe there's a line that fits through here. Maybe there isn't. But we can sort of test whether it seems reasonable for there to have been a line that fits through here. Is there a linear relationship between x and y when we get this ordered pairs of data? Does that make sense? And so the question is, how should you, so this line has some equation, y equals alpha plus beta x. Maybe you prefer mx plus b as the equation of a line. Same thing, I just changed the letters. Can you see, is that big enough? So let's say we assume the regression of y and x is indeed linear. We're going to try to fit a line through a whole bunch of points. How do you do this to optimize something? Well, what should you optimize? I guess you would like to optimize, you see, what do I have? So what should we optimize? What should we optimize? Or what are our errors? What are the errors? So if the true equation is this, if the line really is this relationship, then let's look at this particular point, y17, x17. Here's a point. Well, the line says it should be this point. What should that point be? The value here is whatever the x value is, x17. The true value should be alpha plus beta times x17. That should be the value of y. Does everybody see that? This place on the line is the y value when x is equal to x17. But that's not what the y value is. The y value is y17. So that's an error. Okay? So each of these errors, each error looks like alpha plus beta xi minus yi. This is where what the y value should be. This is what the y value truly is.
Of course, we don't want them to cancel out, right, with negative values.
Exactly. So if we just add up all of these values, we'll have the same problem we had before, where large negative values will be canceled by large positive values, and we won't be able to tell the difference. We won't be able to tell if we've chosen a good value for alpha and beta. So what does Lissandra decide to do? Take the squares, okay? So an old idea of Lissandra, optimize the sum, not just of the errors, but the squares of the errors. Let me write the negative of what I wrote here. Things will come out a little bit more convenient. So this is a quadratic form. Well, it's a quadratic polynomial in alpha and beta. And what we should minimize, by optimize I mean minimize, because this is the total error, sum of the squares of the error. Okay? You could put a 1 over n, you could say the average, but it doesn't matter. It's just some constant times this thing. We're trying to minimize this thing. Is that clear? Is that clear how you would come up with this? Is it clear what geometrically this is measuring? So each of these points should be where the line says it is. That vertical distance is the error. Okay? And we want to square the errors so that the positive and negative signs don't cancel, and so that we have nice derivatives. Squaring is a nice function that collapses positive and negative things. Why do we want nice derivatives? How are we going to optimize this function? If it's truly at its minimum,
The partials should vanish.
then if I wiggle alpha a little bit, it gets bigger. Or if I wiggle beta a little bit, it gets bigger. So exactly as Zach said, the partial derivatives should vanish. So to find minimum, to find the minimum of q, solve the partial derivative of q with respect to alpha should vanish, as should the partial derivative of q with respect to beta. That will give us estimators, least squares estimators for alpha and beta in terms of the data. Is that clear? So this will give what are called it's the method of least squares. So using the method of least square error estimators. Estimators alpha hat, beta hat. Alpha hat and beta hat will be functions of the observation, the xi and the yi. We observed xi, yi. This is the best value of alpha and beta you should take given the outcome of the observation if you think that the relationship is linear. If the regression is linear. Does that make sense? Any questions? Let's do it. Okay? This is not going to be a hard thing to do. So let's differentiate q with respect to alpha. Q is right here. So I get a summation. I goes from 1 to n. The derivative of this thing squared, the 2 comes down. 2 yi plus, I guess not plus, minus alpha plus beta xi. The square is now a first power. And I need a chain rule. The derivative of this with respect to alpha is -1. The only place it appears is here, -1. So the chain rule term is -1, and I'm going to set this equal to 0. Okay? That -1 is a constant everywhere. That 2 is a constant everywhere. I can multiply the whole equation by -1/2. So this is equivalent to the sum of the yi I can write as n y bar being the average value of the y's, minus, I get alpha. How many times do I get alpha? N. Everybody see that? N alpha. Minus beta times the sum of the xi. Nx bar, beautiful. Nx bar equals 0. Does everybody see that? So the -1 and the 2 we can just drop right away. The sum of the yi is ny bar, minus alpha. How many times do I get alpha? N, minus beta, which is a constant, pulls out of the sum. I have a sum of the xi, that's nx bar. Now I can cancel the n's. Okay? So that happens if and only if alpha plus beta x bar is equal to y bar. Does this equation make sense? Why does it make sense? Nikki? It's the same formula, right? We're trying to see if individually y should be linear in terms of x. Well, if so, then the average value of y should be the linear, have a linear relation to the average value of x. Because linear things average to linear things. Okay, that's one equation. The other equation we need is that the beta derivative vanishes. So let's compute the derivative of q with respect to beta being 0. So you can still see q? No, you can't see q anymore. Let me put q, let me put it like that. Okay. Yeah, it's a little good. Okay, so now we're differentiating with respect to beta. We still get a sum as I goes from 1 to n. We still get a 2 yi minus alpha plus beta xi to the first power instead of squared. And the chain rule term is now negative beta. Negative xi, okay? Be careful with your derivatives. You're differentiating with respect to beta. Negative xi is the chain rule term of the partial derivative. Negative xi. So this whole sum equals 0. Does everybody see that derivative? Okay, great. The 2, again, is everywhere. We can cancel it. The negative sign is, again, everywhere. We can cancel it. And so we have this equation. So let's see. What can we do? Well, let's just work it out. So I have a summation as I goes from 1 to n of yi xi. Summation as I goes from 1 to n of xi yi. That's one term. Minus, I have an alpha. And what is alpha being multiplied by? Xi. And I'm summing from 1 to n, nx bar. Okay? Minus beta. And what's beta being multiplied by? The sum of the squares. Xi squared. An xi there and an xi there. As I goes from 1 to n. And this equals 0. In other words, I can move these two negative signs to the other side and I get this relationship. Slightly more complicated relationship. Okay? Does everybody see that? Now, it will be convenient to introduce certain notations. So let's introduce some notation. Let S, X, Y, by definition, be the sum as I goes from 1 to n. I'm going to mimic covariance. Xi minus x bar times yi minus y bar. If I average 1 over n or 1 over n minus 1, depending on, or actually 1 over n minus 2, as we'll see in a minute, I'm just defining something. So the notation SXY means take xi, subtract off its mean, take yi, subtract off its mean, multiply the two, and sum, not average, sum. So if I open up this product, I will get xi, yi. I'll get a minus y bar times the sum of the xi's. That's nx bar, y bar. I get minus x bar times yi times the sum of the yi's. That's another minus n x bar, y bar. And I get a plus x bar, y bar, and I get that n times. So if I did that too fast, just think about it at home. We've done this 100 times. What's left over, so I get minus 2 plus 1, so I get minus 1 and x bar, y bar. So if I did that too fast, try it again at home, make sure you get the same answer. Okay? And for the same reason, I'll introduce SXX, which is the same thing, just instead of x's, instead of y's, I'll put x's. In other words, xi minus x bar squared. So this is some unnormalized variance, and for the same reason as before, as in fact it's the same exact argument, here I get xi squared minus n times x bar squared. So far so good, everybody's with me? Okay, so let's turn this equation into something a little bit more, a little bit easier to write down. So what is the sum of xi, yi? Sum of xi, yi is here. So it's sxy plus n x bar, y bar. Does everybody see that? So on this side, I get sxy plus n x bar, y bar. On the other side, well, that have an alpha n x bar, nothing I should do about that, plus beta. And what is the sum of the squares of the xi's? Sxx plus n x bar squared. Everybody see that? So I'm replacing this with this. Sxx plus n x bar squared. It looks like a complicated equation. We're going to see in a second what's going on. Let's combine this equation with that equation, the first equation from the partial derivative with respect to alpha being 0. Right? We need to solve the pair of equations. Alpha plus beta x bar is equal to y bar. Alpha plus beta x bar is equal to y bar. That's just the equation up there. And this one, which was a simplified version of that one. Okay? So we solve these two equations together. Any suggestions for what we could do?
Solve for alpha first.
We could solve for alpha, or we could multiply both sides by nx bar and subtract. Okay, so if I multiply by n x bar, n x bar, n x bar, and I subtract the two equations, something nice happens. What do I get on this side?
SXY.
Sxy. What do I get on this side? These two are gone.
Beta times SXX.
And beta negative n x squared, this cancels this, and I just get beta sxx. In other words, beta is equal to sxy divided by sxx. That's beta hat. Okay, this again is something you purely compute based on the outcome. The outcomes, I got a bunch of xi's and I got a bunch of yi's. From that I compute the average, x bar and y bar. So then I just plug everything in. I get a number for this. I get a number for this. That is the best slope. That's my beta. That's the best slope I can come up with. What is alpha bar? What's the best alpha I can come up with? The original equation was alpha plus beta x bar is equal to y bar. Let me isolate alpha, y bar minus beta x bar. And I know what beta is. Beta is this. So alpha is equal to y bar minus sxy over sxx x bar. Does everybody see that calculation? So that is the method of least squares best estimators for the slope and the intercept. Do these values make sense? We've done a whole computation. Let's come back to the beginning. Do these values make sense? How do I show you both of these things at once? I think I can do this. Or even better, this. The point is, what we did before is we said if there is a linear relationship, then that linear relationship is nu minus mu c over sigma squared plus c sigma squared x, right? Alpha was supposed to be the expected value of y minus the expected value of x times the covariance divided by the variance of x. And look at what we've done. The optimal alpha is the mean of the y's that we observed minus the mean of the x's we observed times, well, these aren't normalized, but whatever the normalization is for both of them cancels out. So this is effectively the covariance divided by the variance of x. That's the best value of alpha, exactly as it was here. Best value of beta, covariance divided by variance. Empirical. Observed. Okay? Does everybody see that? So no great mystery there. So I hope that makes sense to you. So again, what have we done? Let's review. First, we understood what happens in general for a linear regression. This is what the relationship must be if it is indeed linear. Then we said, okay, well, how would we, this was just probability theory, how do we do some statistics on it? We observe a bunch of values. What is the best line that we can fit through it? Lissandra's idea is to minimize the sum of the squares of the errors from where it should be to where the line would say it is. From where it is to where the line would say it should be. That's this distance. How do we compute that? Calculus. We took partial derivatives with respect to alpha and beta, set them equal to 0, did a little bit of manipulation, and found these optimal values of beta hat and alpha hat. Any questions? Okay. Very good. So the question is, how good are these estimates? So these are estimators. We got these estimators, but how good are alpha hat and beta hat as estimators for alpha and beta? Well, if I don't know anything about the distribution of x and y, I basically have no chance about saying something about how much these numbers fluctuate in general terms. So let's take it one step further. To take it one step further, we need an extra assumption. Let's assume that the relationship of y on x is normal. Okay? Extra assumption, and this is sometimes called a normal regression, often called a normal linear regression analysis, says that this, let's look at the density function of y given a known value of x. Right? This is the conditional density. This is the conditional density. Bless you. And let's make the assumption that this is normal. Okay? So it's normal e to the minus y minus its mean squared over 2 sigma squared, less u normalized by 2 pi sigma squared. But the mean, we're assuming that we have a linear regression. So what should the mean value of y be, assuming x? Other than Ernst. The conditional, remember, what does it mean that we're looking at linear regressions? We're assuming that the conditional expectation of y on x is alpha plus beta x. This is conditional expectation as opposed to conditional density. This is the mean, right? This is the expected value of y if we know what x is. So what's the mean value of y if we know what x is? Nikki? Exactly. It's alpha plus beta x, right? That's what Ernest was going to say, I assume.
Yeah.
Alpha plus beta x. Does everyone see how the extra assumption of normality is this shape? Okay? Now, so if that's what our assumption is on the shape of this conditional density function, well, we have another way that we can compute alpha and beta and sigma, or at least estimators for this. Once we know what the density function actually looks like, we can use the maximal likelihood method. This is going to be a great review of everything that we've been doing throughout the semester. So, given this extra assumption, with this extra assumption, can compute the maximum likelihood estimators for alpha hat, beta hat, and sigma hat. There are 3 parameters here that we don't know. We don't know alpha, we don't know beta, we don't know sigma. But we saw a bunch of data, right? We observed xi, yi, these pairs. We think of the xi as being given to us, and what is the distribution of the yi given a value of xi? It's this. So the likelihood of seeing y1 through yn given the values of x1 through xn and the value of alpha, beta, and sigma will be what? How do we compute this likelihood function? Just multiply all of these together. Exactly? Exactly. Okay? 1 over root 2 pi sigma squared times e to the minus y1 minus alpha minus plus beta x1 squared over 2 sigma squared. And then the same one for 2 and 3 and so on. So there will be n of these. And then there will be a product as I goes from 1 to n of yi minus alpha minus beta xi squared over 2 sigma squared. Can you guys see that? That's the likelihood function. How are we going to maximize the likelihood function? Take the derivatives and set them equal to 0, right? The derivatives of this will be nice or not so nice? Not so nice? Well, depends on your definition of nice. There's an easier thing we can do with likelihood method, which is often convenient when we have exponentials. Take the logs, okay? So, if we want to find the partials being 0 with respect to all of the variables, alpha, beta, and theta, all the parameters that we're trying to estimate, it's equivalent to doing the same with log L. So let's work out what log L is. Log L. All right. So I have this 2 pi. So I'll have a log 2 pi to the nth power. So the n comes down, and actually it's in the denominator, so it's a minus n, and it's actually square root, so it's the square root I can take out as a factor of a half. Okay, so minus n over 2 log of 2 pi takes care of the 2 pi. How about the sigma squared? I have a minus n log of sigma squared and square rooted, so it's just log sigma. Minus n log sigma. That's that term. Log of a product is a sum of the logs. The log of e to the something is just the something. So what do I have here? I guess I can put a minus sign. That minus sign I can put there. yi minus alpha plus beta xi squared over 2 sigma squared, which maybe I can pull out here if I have room. 1 over 2 sigma squared with a minus sign. And then I don't need a denominator. So again, the log likelihood function is some constant, log 2 pi negative n over 2. I mean, n is fixed, so 2 pi is a constant. Minus n log sigma minus 1 over 2 sigma squared. The sum as I goes from 1 to n, the observed value of y minus the expected observed value of y, namely alpha plus beta xi, quantity squared. Hey, that's the sum of squares. That's Lissandra's sum of squares formula. So guess what will happen when we take the derivative with respect to alpha and set it equal to 0, and do the same with the derivative of beta.
It's the same thing as minimizing the sum of squares error.
Exactly, because there's no alpha or beta here. These things both go to 0. And this is just a constant, so that doesn't at all change the minimal value of alpha and beta that was observed in the sum of squares. Okay? Implies alpha hat and beta hat as before. So the maximum likelihood estimator for alpha hat and beta hat is exactly the same as the least squares estimator for alpha hat and beta. What about sigma? Now we have something to do. So let's look at d log L d sigma and set that equal to 0. So there's no sigma here. Here I get, can you guys see? What do I get when I differentiate this term with respect to sigma? Sorry, say it again. This is negative n log sigma. So derivative of log sigma is 1 over sigma, right? We're differentiating with respect to sigma. So I get a negative n over sigma. And here I get a negative, well, this is sigma to the minus 2. So if I differentiate sigma to the minus 2, a minus 2 comes down, kills off the minus a half, leaves a plus sigma to the minus 3, 1 over sigma cubed. Times, and all of this is a constant as far as sigma is concerned. As I goes from 1 to n, yi minus alpha plus beta xi squared. And that's equal to 0. So how can that be? Well, let me put things over a common denominator. I'll multiply this by sigma squared so that I get a sigma cubed there. Now I can multiply through by sigma cubed. And what I get is, let's slide this up. Okay, this is where we were. So I'm dropping the sigma cubed, so let me move this n sigma to the other side, so I get n sigma squared is equal to a sum, as I goes from 1 to n, of yi minus alpha plus beta xi squared. In other words, sigma squared is 1 over n times this thing. In other words, sigma is the square root of this whole thing. And sigma is now sigma hat, our estimator for sigma. where what is alpha and beta? Alpha hat and beta hat. Okay? So again, yeah, it's an exercise. Let me leave it as an exercise. This, if you stick in the values of alpha hat and beta hat, then what you will get here is square root 1 over n of SYY. So this is like the variance of y minus beta hat SXY. And beta hat was SXY over SXX, so it's like the covariance squared. This is just algebra. Stick in the actual values here, pull together the sums, everything will square out to this. Okay? So we have our values of alpha, we have our values of beta. We get the same estimators from the maximum likelihood method. Now we also get an estimator for sigma hat. Does that make sense? All right. So, how can we try to test certain hypotheses? Now that we have some distribution that tells us what the expected variance will be given the observations, we can start getting confidence intervals and p-values and all that other good stuff that we've been doing. Okay? So to test hypotheses, so again, under this assumption, so what do? We assume we have this extra information, this normal regression analysis, that the dependence of y on x, that the conditional density of y on a known, if we know the value of x, what is the density of y? It's just a normal where the mean is what it's supposed to be, the linear relationship between y and x. We constructed the likelihood function and solved for the resulting estimators on the parameters. The alpha and beta parameters had exactly the same estimates as before because it boiled down to a least squares error. And sigma squared, we got another expression for, which was given here. So let's test under this normality assumption, various things, properties or hypotheses on these parameters. The most important hypothesis you would want to test, so for example, why would I want to test beta hat equals 0? This is a good test of your understanding of all these symbols. What does beta hat represent?
Like correlation between x and y.
Exactly. Beta hat is the slope, right? Remember this data plot? Here's our scatter plot. What if the slope looks flat? Beta hat, by the way, was SXY over SXX. This is the correlation. Right? If the optimal line is a horizontal line, a line A alpha plus beta x where beta is 0, it's just a straight line across, that means the value of y in no way depends on the value of x. It's that they're uncorrelated, right? That there is no actual correlation. This would be the null hypothesis. We want to show that they're correlated, so we'll test whether they're uncorrelated as a null hypothesis. So this would be a null hypothesis if we want to show that there is a correlation. If we want to show, on the contrary, that the variables are correlated. Okay? Does that make sense? So, all right. So how would we do this? So remember what beta hat is. I have it right here. It's SXY. SXY is a sum as I goes from 1 to n of xi minus x bar times yi minus y bar. These are the observed values over SXX. So what we want to do is, instead of thinking about the observed values, think about the random variable that these observed values came from. So little xi, little yi are the observed values, and this is our estimator for beta. What big yi is the random variable that these observed values came from. So let big B hat be exactly this expression where I replace yi, the observed value, by the random variable. So this is now a random variable itself. So it's a sum as I goes from 1 to n. This thing I'm going to pull inside so that I have a nice clean xi minus x bar over sxx. These are coefficients. Okay, so these are still observed values times the random variable yi minus the sum of the yi divided by n, which I'll continue to call capital Y bar. So instead of being an estimator, estimator is given these outcomes, what's my best guess for this parameter? This is now a random variable. I have these random variables. I'm going to multiply them by these coefficients, which I assume are known, and I sum them up, and that will be a new random variable. Does that make sense? The distinction between these two? Taylor, something?
No, I'm just thinking.
Okay. Okay? Everybody's happy?
Yes.
So this is now a random variable. What is this random variable? By the way, there's another expression for this random variable, slightly nicer one. I claim that this is equal to a sum as I goes from, let's see, 1 to n, xi minus x bar over sxx times just the yi's themselves. Why is that true? Ernest?
Is it because the xi minus x bar, when you sum them up, it's going to be 0?
It's going to have mean 0.
And you can actually take out the y bar, so the second term disappears.
The y bar doesn't depend on I, so the y bar, if you open up this sum, if you multiply, so yi times this is exactly what we have, minus y bar times this, but y bar is a constant, doesn't depend on I, so it pulls out of the I, so does sxx, and now I have a sum of the xi, which will be nx bar, minus nx bar. Okay, so that's one nice little observation, but it doesn't matter so much. What have we assumed about the yi as random variables given the known values of the xi? They are normal, right? We're doing normal regression analysis. So these are normal. I have some fixed constants. I don't know anything about the xi's. The xi's I've observed. I have some fixed constants. I add up normal variables. What's the sum of normal variables? Normal. Okay, so this is normal. So I only need to know two things to pin down exactly what the distribution of a normal random variable is. I need to pin down its
Mean.
all together now, right? We've been doing this a long time. Yes. We know we need to specify a normal variable exactly. We need to know its mean and its variance. So need to know what the mean, and variance of this random variable B hat is. All right, so let's compute its expected value. Is everybody following along? Is anybody lost? We're throwing a lot of new things at you today, but they're all things that are at least somewhat familiar from previous things we've done. So we had a linear regression, then we assumed normality, we did a maximum likelihood estimate, we found the sigma and beta and alpha hat, the estimators. Now we're going to replace the estimator value by the random variable, and now we need to compute the expected value of this random variable. Right? Everybody see that? And again, this is all assuming that we know the values of the xi, that the values of the xi have been given to us. So if you like, you can write expected value of the beta I, given that we know what the xi are. But I'll usually suppress this now. Okay, so if we know what the xi are, then these are all constants. So this is a sum as I goes from 1 to n, xi minus x bar over the variance, or some version of the variance, times the expected value of the yi given the xi. What's the expected value of the yi given the xi? Theoretically. Dylan.
Alpha plus beta.
Exactly. We're assuming a linear regression. By definition, this should be alpha plus beta xi. Alpha and beta or alpha hat and beta hat? Let's test our understanding of the distinction. Why alpha beta, Justin?
I don't think we're ready to use the hat yet.
Say it again.
I don't think we're at that stage.
So the point is, we are assuming that the random variables are distributed according to a law with some unknown parameters. When we're doing a theoretical calculation like this, we're allowed to use the unknown parameters. Even if we don't know what alpha and beta are, the outcome, this expected value, is in terms of alpha and beta. When we're trying to estimate alpha and beta, given the outcome of an experiment, then we use alpha hat beta hat. Everybody understand the distinction? So these are the true parameters, we just don't know what they are.
Can you just repeat that again?
Yes. So this is a random variable. We're assuming that the distribution of this random variable, conditioned on the value of the xi, is a normal with mean alpha plus beta xi. So we're assuming that we have this linear regression of y on x. Do you see that, Jess and D? If I put alpha hat and beta hat here, that means what is my best estimate for what the true value of alpha and beta are. If I just put alpha and beta, it means what is the true value of alpha and beta, even if we have no right to know that true value, or we don't know what that true value, we're trying to estimate that true value. Does that make sense? Okay, that's the expected value. Let's start playing with it. Should I leave this as an exercise, or should I do it with you? Am I giving you too many exercises to check your understanding? All right, let's do it together. First thing I claim is that you can get rid of the alpha. Alpha is a constant. I'm going to multiply it by all this stuff and add. This has mean 0 already. So for the same reason that we could drop the y bar, we can drop the alpha. Does everybody see that? Alpha doesn't have any i's in it. So the step one is that this is equal to, exactly equal to, a sum as I goes from 1 to n, from 1 to n, xi minus x bar over sxx, times beta, which is a constant, times xi. Okay? So I have this beta, which is a constant. By the way, this sxx is also a constant. This variance of x looking term. And what's left over is a sum as I goes from 1 to n of the xi squared minus a sum, so x bar is a constant, times the sum of the xi, which is nx bar. Does everybody see that? So first, this doesn't have any i's in it, so it comes out of the sum. So that's beta over sxx. This was this variance looking term. Then I have xi times xi is xi squared, minus x bar, which is a constant, times the sum of the xi's. Justin.
Why does the alpha go away again?
Why did the alpha go away again? For the same reason that the y bar up there went away. So if we take this alpha and we look at the sum, well, alpha is a constant, it comes out. Sxx also comes out. And now I have a sum of the xi, which is nx bar, minus x bar, which I get n times. Sum So I get nx bar minus nx bar. Okay? Or more philosophically, this has mean 0 and is just a constant and I'm summing. Okay? Is everybody happy with this so far? What's SXX? Dylan?
Second term, same thing.
This whole second term, yes. This whole thing was literally what SXX came out to be when we did our computation before. SXX, initially defined as a sum of xi minus x bar squared, is the sum of the squares of the xi minus n times x bar squared, which is exactly what we're seeing, this is what xxx, this is the definition. An easy calculation gave us this, and that's exactly what we're seeing here. Sum of the xi squared minus n x bar squared. So that's SXX, and this is XXX in the denominator. So the expected value of B hat is just bigger. Everybody see that? This whole thing, let's just make this abundantly clear, this whole thing literally is SXX. So it cancels top and bottom. That's great. We have a random variable. I mean, was that unexpected? We have this random variable B hat. It's the random variable that we're trying to mimic what beta is doing. We're trying to understand what beta, the estimator, is as a random variable. And it's a normal random variable, and its mean is literally beta. Perfect. It's supposed to be beta. Does that make sense? What are we going to compute next?
Variance.
The variance. You guys want a little head start? You want to take 5 minutes and see if you can compute the variance yourselves? We have a few minutes, not too many. Let's take, so step 2, next, we want to compute the variance of B hat. Remember, this is the definition of B. How do I not cover this up? Okay. So here's the definition of B. These are just numbers. And we want to compute the variance of B hat. It's good. Everybody's hard at work. Earnest.
Should we assume that every observation is independent? Or does it matter?
Yes, we are assuming that the yi's are independent of each other. I like to see all the pencils going. What was your first step? Dylan.
Using E of beta squared for B squared.
Using, say it again?
So the formula of E of B squared minus E of B squared is variance. Time that.
Oh, you're going to do expected value of B squared?
Yeah.
You could do that. That'll be more complicated. The question was, are these guys independent? And the answer was yes. So we have a sum of some constants times independent variables. So the variance will be just the constants squared times the variances of the variables. Right? So that's a slightly... sometimes that technique works better. Sometimes the more direct thing works better. So I have my constants squared, xi minus x bar over sxx squared times the expected value, sorry, times the variance of the yi variables. Does everybody see that? What is the variance of the yi variables?
Sigma squared.
Sigma squared, right? This parameter that we, again, it's not sigma hat squared, it's sigma squared. We don't know sigma. This is sigma squared, the unknown theoretical parameter. Okay, does everybody see that? Now let's mess with this a little bit. Let's try to simplify. So I get a sigma squared. There's this sxx squared in the denominator, and then I get a sum as I goes from 1 to n of xi minus x bar squared. What is this? Yeah? It's SXX. It's the very definition of SXX. Right? The covariance of x with itself. In other words, the variance of x. Unnormalized. And so the variance of B hat is sigma squared. There were two of them here, and there's one in the numerator, so we get one in the denominator. One SXX in the denominator. So again, let's recap. Beta hat, I mean B hat, this random variable B hat, which is defined as a sum as I goes from 1 to n, xi minus x bar over sxx, these are all things we observe, times the random variable yi, even though really it was yi minus y bar, but it's the same thing. That random variable is normal. This is a normal random variable with mean expected value of B hat being this theoretical value beta, and variance of B hat is exactly what we just computed, the theoretical sigma squared over sxx. All right. In the interest of time, let me state a fact whose proof is very similar to proofs of things that we've discussed already. When you look at this sigma hat estimator, remember what sigma hat was? Remember sigma hat? We computed this estimator from the maximum likelihood estimation. Sigma hat was this thing. So that, as a random variable, who's with y as the random variable, as a random variable function of y's, this, so fact is that sigma squared times n, which is s y y. How do I do this so that you can see and I can write? Let me try that. There we go. Okay, you can see sigma squared. You can see sigma hat is this. So n sigma squared, which is syy minus beta hat, which I'll write as b hat, s little x capital Y. This divided by the true sigma squared, so 1 over the true sigma squared of this thing. It's an unwieldy calculation, but what do you think the distribution of that is? The yi's are normal, and I'm multiplying the yi's against each other, and I'm subtracting some linear term in the yi's, x times y. What does your intuition say this random variable should be? You sum a bunch of squares of normals. Chi squared. Okay. So this is indeed, this random variable is a chi-squared distribution, it turns out it's not n minus 1 degrees of freedom, it's n minus 2 degrees of freedom. Okay, that's a calculation that I will omit. And one more fact, and another fact, is that this variable, n sigma squared over the true sigma squared, sorry, sigma hat squared, over the true sigma squared is an independent, as a random variable, is independent of B hat. Okay? So these are two facts that I hope are familiar from what we had been doing before, even if I'm not providing the full proof. So if that's the case, if you allow me this fact, then oh, I see what's going on. If I do this, then I can both show you what I think you're seeing and what you're actually seeing. There we go. Okay. So B is a random variable. It's normal. That's its mean. This is its variance. N sigma hat squared over sigma squared is chi-squared with n minus 2 degrees of freedom. That means I can make a, given a Gaussian and a chi-squared that are independent, I can construct a t variable. So what's my t variable? I need a normalized Gaussian. Where do I get a normalized Gaussian from? B hat. What's its mean? Beta. What's its variance? Sigma squared over SXX. And if I divide this by the square root of a chi-squared random variable divided by its degrees of freedom, so what's the degrees of freedom of my chi-squared variable? N minus 2, and I'm dividing in the denominator, so that's the same as multiplying by n minus 2. Right? Remember what t is? It's z over root, can I call this y? I can call it y, right? You guys will be okay with that. Y over n. So that root n goes in the numerator. N was the degrees of freedom. This y is not that y. That's why I'm hesitating to use y. But you know what's going on. Okay, and what's my chi-squared random variable? This thing, n sigma hat squared, which is this thing. So if I put this in the denominator, that's a sigma squared in the numerator. Sigma squared in the numerator. SYY. Let me just write n sigma hat squared, so I don't have to carry all that around. Opening this up was just to show you why it should be a chi-squared. It's a sum of squares of Gaussians. So this is 1 over a chi-squared random variable divided by its degrees of freedom, square rooted, and this is a Gaussian. And the beautiful thing that happens that we've seen time and time again is that this unknown parameter sigma cancels out. The unknown parameter sigma cancels out. This is now a standard t. This is a t distribution. This is a t with n minus 2 degrees of freedom. And it's just in terms of everything that is computable or estimatable and the one parameter. Okay? So let's do all the things that we're used to doing. Let's give a so theorem. Let's take this as a theorem. Theorem B hat minus beta. Let's clean this up a little bit. Times this SXX is going to go in the numerator. Times SXX times n minus 2 divided by sigma hat squared times n is a t distributed random variable with n minus 2 degrees of freedom. I'm writing where you can't see and no one's telling me anything. Come on, guys. You see that, right? So, B hat minus beta. Beta is our unknown parameter. B hat we can estimate from, we have this estimator, beta hat. Sigma squared, we can estimate. These are all functions of the data. This is the only thing that's not a function of the data. So we can give a confidence interval. We can give a p-value to an observation, right? So let's construct. So construct, here's a question. Construct a 1 minus alpha times 100% confidence interval for beta. Remember, beta is the slope. We're trying to determine whether the slope could be 0, whether the y observation and the x observation could be uncorrelated, assuming that they are normally and linearly, that the regression of y on x is normal and linear. Right? So how could we do this? What does the t-distribution look like? It's a Gaussian over chi-squared, so it looks like a Gaussian. And then I want to cut off alpha over 2, two-sided. I didn't specify the confidence interval. So I want to cut off alpha over 2 of the mass on both sides. This number is T sub alpha over 2 with n minus 2 degrees of freedom. So the probability that this thing, beta hat minus beta times square root of n minus 2 over n sxx over sigma hat squared. The probability that this thing lies between t alpha over 2 n minus 2 and negative t alpha over 2 n minus 2. Probability of this event is that we're in the bulk, 1 minus alpha. That's our 1 minus alpha confidence interval. And now we need this in terms of beta. So I multiply through by this, and I move beta to the other side. This interval is equivalent to beta lying between b hat plus something and b hat minus something. That something is the same thing. What is that thing? T alpha over 2 n minus 2 times 1 over, this gets multiplied to the other side, so it's the square root of n sigma hat squared over n minus 2 sxx. And this same thing there. And if with 95% certainty this interval, this 95% confidence interval does not contain 0, then the null hypothesis that your y variable is uncorrelated to the x variable should be rejected. Any questions? So we did a lot. This was a very, I look around and I see confused faces. We did a very large sampling of all of the things we've been doing all semester long. So let's just review for 1 minute, right? Let's go over everything. What did we do? 3, 2, 1. Okay? Let's look at this one more time. We started with an assumption. This was a general discussion about linear regressions. What do we know about linear regressions? If the regression happens to be linear, then we know what the slope and the y-intercept must be. That's just pure probability theory. What should we do given observations? Optimize a sum of the squares of the errors, least square error. This is Lissandra's method. We set up this error. We took the derivatives with respect to alpha and beta, solved for optimal values of alpha and beta. And it turned out that the optimal values of alpha and beta were exactly the same shape as the theoretical values of alpha and beta, namely the mean value of y minus the mean value of x times the covariance divided by the variance of x was the y-intercept. The slope was the covariance divided by the variance of x. Then we took it another step further and said, if we want to know something, this was again completely general, just assuming that we have a linear relation, that the regression is linear. The regression of y on x is linear. If we want to know more, we need an extra assumption. The extra assumption is that the regression is normal. What does it mean to be normal? It's that the conditional density of y for a given value of x is Gaussian. We don't know what the variance is. The mean is assumed to be the expected, the conditional expected value is linear, okay? The conditional expectation. And then we use the method of maximum likelihood to solve for alpha hat and beta hat, which came out to be exactly the same equation, not only the same solution, the same equation. And but then there was another equation to solve for sigma. That gave us values of a new value, which is sigma hat, which is an estimator for sigma. And then the question is, how do we test some hypothesis based on these estimators? Because we know normality, we've assumed normality. So if we want to test, for example, beta equals 0, we need a confidence interval, which means we need to know what this as a random variable. So I'm going to change notation from just the value that we see empirically to the random value, the random variable of that value, that value comes from. Okay, this is a subtle distinction that I hope you guys are okay with. Okay, these are just the observations. Those observations came from a random variable. This is the random variable which takes the same linear combination of the observations as the estimator. Okay, we saw that this variable is normal. We needed to compute its mean and its variance, which we did. So now this thing is indeed a normal random variable. To get a t, we need a chi-squared, because this normal random variable has a parameter in it that we also don't know. We don't know beta, its mean. We don't know sigma squared, but we can get rid of it by using sigma hat squared, and this turns out to be properly normalized, exactly a chi-squared random variable, and it's independent of beta hat. So we're in position to turn this into a t random variable. When we do that, we can get confidence intervals for beta in the standard way. So as a whirlwind, this is kind of a good review of all the different things, all the different techniques we've been learning applied to one particular problem. Any questions?